So to predict the relative ionic character of chemical bonds, we're going to classify whether something is pure covalent, whether it is polar covalent, or whether it is ionic. And actually, in Gen Chem, there is another part of the spectrum that we haven't really discussed. So I'll kind of allude to it a little bit because for some of these questions, you kind of need to talk about it. So on the scale between pure covalent and polar covalent, where we have uneven sharing of charge. General chemistry makes you think it goes all the way up to like just pure ionic, but actually there is another grey area in between that you won't really deal with until you get into inorganic chemistry, which is where you have, I'm just going to call it covalent character, and I've really stuffed up my boxes here. Covalent character. So in the same way the polar covalent bonds are like, ooh, a little bit ionic because we have a little bit of charge separation. In between polar covalent and pure ionic, we also have this covalent character area, which is arising from where you have like a small highly charged cation, so that you've got all your positive charge in like a small place, and then you've got a big fat smushy anion, which is what we call polarizable. So the effect of this small highly charged cation and this big squishy negatively charged anion is that the electron cloud gets distorted around the anion, so it acts a little bit more covalently than if it was pure ionic. So we don't need to know this for like Gen Chem 1, but it's in there. Okay, so if you're like looking at two different compounds and being like, well, they're both ionic, just remember there is percent and degrees of ionic character as well as covalent character. Okay, so first up we've got oxygen. It's bonded to itself, so there is no electronegativity difference. So that has to be non-polar. Okay. Magnesium oxide. Magnesium is a metal. Oxygen is a non-metal. Okay, so that is, we're going to predict that is going to be ionic. Okay. Strontium is a metal. Oxygen is a non-metal. So we're also predicting that to be ionic. And silicon dioxide, silicon and oxygen. Well, silicon's technically a metalloid, but I'm going to still predict covalent bonding here. So we're going to predict covalent bonding, but it's probably polar covalent. If you want to know for sure, you can check the numbers, okay? So just looking at the positions of all these on the periodic table as well, we've got oxygen over here, we've got magnesium over here, we've got strontium over here, and then silicon here. So in terms of like the biggest difference in electronegativity, it's going to be between oxygen and strontium. So I would predict strontium oxide to be the most ionic. Yes, so we're going from most ionic to least ionic. Okay. And then magnesium oxide to be slightly less ionic. It's still technically ionic, although the melting point of magnesium oxide is considerably lower than the melting point of strontium oxide. And as you might have heard mentioned before in class, whether you remember or not, ionic compounds have got higher melting points than covalent compounds. So the fact that magnesium oxide has a significantly lower melting point than strontium oxide also tells you that there is some degree of covalent character in the magnesium oxygen bonds. Anyway, this is me as an inorganic chemist getting excited, but I'm jumping the gun a bit here. And then you've got your silicon dioxide, which is mostly polar covalent, and then lastly you'll have your oxygen, which is bonded to itself, so that's got to be pure covalent. So if you wanted to, you could also look at the differences in the electronegativity values just to convince yourself that you are barking up the right tree. Come here, table. Okay. So if you look between strontium 1.0 and oxygen, that's an electronegativity difference of 2.5, but between magnesium and oxygen, that would be a difference of 2.3. Okay, so slightly less difference in electronegativity. Then silicon and oxygen, 1.8 versus 3.5, so that's going to be again a considerable difference in electronegativity. Okay, 1.7, so it's polar covalent just about, and then oxygen versus oxygen, obviously it's the same. So there you go.